Welcome to the another episode of learning. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem from the section Linear Algebra that has appeared in the CSIR National Eligibility Test held on December 15, 2019. The given question is related to linear transformation, and this question is placed in part C, which is a multiple select question. There can be more than one answer, and the question carries 4.75 marks. The question ID is 187-980-1813. This question is suitable for all these examinations. Right. The given question is, let T be a linear transformation from C power n to C power n, that is the complex n space to complex n space, where n greater than or equal to 2. Suppose that 1 is the only eigenvalue of T. Which of the following statements are true? We are given 4 options. Option 1, T power k is not equal to identity for any k belongs to n. Option 2, T minus I to the power of n minus 1 is equal to the 0 matrix. Option 3, T minus I to the power of n is equal to the 0 matrix. Option 4, T minus I to the power of n plus 1 is equal to 0 matrix. So, we are given 1 is the only eigenvalue of T, that is the crucial one, what we have to consider. We now discuss the solution of the problem in detail. We have a linear operator T from the complex n space into itself, where n greater than or equal to 2. Right. We look at the option 1. Now, is there corresponding to every linear transformation, there will be an underlying matrix. Therefore, we will think in terms of the matrix associated with the T. So there is no loss of generality in doing that one. So T power k not equal to I for any k belongs to n. This is not true. Suppose you take the matrix corresponding to T is the identity In. That is the identity matrix of order n. What are the eigenvalues of the identity matrix of order n? 1. 1 is the only eigenvalue for I. And when you take T power k, that is I power k, is I only for any k belongs to n. So thus there exists a T such that T power k is not equal to I for any k belongs to n is false. I have shown the example. T power k is identity for all k belongs to n when T is an identity matrix. So that counter example will tell you option 1 is not true. Given 1 is the only eigenvalue of T, okay. So take the option 1, T power k not equal to I for any k belongs to n. Let T be the identity matrix. So clearly 1 is the only eigenvalue of T is equal to In, the identity matrix. But T power k is identity for all k belongs to natural numbers. Identity multiplied by any number of times is identity only. But this contradicts the option 1. So, thus option 1 is not true. So, this is a fact. This is a fact. This is a fact, and what is given is not true. Option 1 is not true for when T is the identity matrix. It's not in general not true. Not true. Right. We move on to the next options. Option 3. T minus I to the power of n is equal to 0 matrix. Option 4. T minus I to the power of n plus 1 is a 0 matrix. Right. And we have that 1 is the only eigenvalue of T. Consider T minus I. Consider T minus I. What are the eigenvalues of T minus I? The eigenvalues of T, 1, minus the eigenvalues of I. They are also 1. So therefore, the eigenvalues are 1 minus 1, 1 minus 1, 1 minus 1 n times. That is 0, 0, 0. So 0 is the only eigenvalue of T minus I. Now you recall, who is that matrix? Where 0 is the only eigenvalue of that matrix? That is a nilpotent operator. So this will imply T minus I is a nilpotent operator of order n greater than or equal to 2. Right. When it is a nilpotent operator, there exists a least positive integer k such that T minus I to the power of k is equal to 0. That is, k is the nilpotent matrix of index k. Index k. So the T minus I to the power of k, where k is the least positive integer such that T minus I to the power of k is 0. When that is so if k is less than or equal to n, so multiply once again by T minus I until you get the power is n. Then you will get T minus I to the power of n is 0. Why all that? When it is a nilpotent matrix, then for any nilpotent matrix, T minus I to the power of n is 0 matrix. So this means T minus I to the power of n, where n is the order of the, where n is the order of the matrix. So you get 0. So thus your option 3 is true. And we have T minus I to the power of n is 0. Multiply again by T minus I. Then you will get T minus I to the power of n plus 1 is equal to 0. Wherever I am saying multiply, it is in terms of matrices. And when you want to interpret in terms of operator T, composing, right? And I have exchanged the words operator and the matrix also, knowingly, because corresponding to every operator we have a matrix. And so I have done that one. Therefore, option 4 is also true. We are left with option 2. T minus I to the power of n minus 1. T minus I to the power of n is 0, certainly. Certainly. Will it be T minus I to the power of n minus 1 is equal to 0? Always? Always? Not necessarily. There exists matrices. You take, let T is equal to 1, 0, 1, 1, 2 by 2 matrix, n is equal to 2, I can take. Then T minus I, 1, 0, 1, 1 minus identity 2 by 2 identity matrix is 0, 0, 1, 0. Now T minus I to the power of n minus 1 is what? T minus I to the power of 2 minus 1. That is T minus I only. But that is not 0. This is 0, 0, 1, 0. Not 0. So this is not always possible, So therefore, option 2 is not true. And the T what we have considered is 1 is the only eigenvalue we have considered. Agreed? So that is the option 2 is not true. Combining all the options, we get the answer as option 3 and 4. Right. I have been giving you an advice from the past 3 or 4 videos that whenever you come across a question look into the question, what are the concepts that are there and what are the theorems that we have used and what are they. While making a notes of it, a little bit of notes, further results about that also you jot down. That will be helpful for the examination. As a sample and as a model, today I will tell you about nilpotent matrices. Right? So we talk about nilpotent matrices. What is a nilpotent matrix? First of all, a square matrix, capital A of order n over R or C, is called a nilpotent matrix if A power k is equal to 0 for some positive integer k, and the smallest of such k is called the index of nilpotence, and k will be less than or equal to n, obviously. The properties of nilpotent matrices. What are the eigenvalues of a nilpotent matrix? All the eigenvalues of a nilpotent matrix, capital A, are 0. When all the eigenvalues are 0, what is the trace? Trace is the sum of all the eigenvalues, therefore 0. What will be the determinant? If one of the eigenvalue of a matrix A is 0, then the determinant of A is 0. Here, for a nilpotent matrix, all the eigenvalues are 0, therefore determinant of A is equal to 0. What is the characteristic polynomial? That will be x to the power of n. What is the minimal polynomial? Is x to the power of k, in this case where k is the index of nilpotency. Triangular form. A nilpotent matrix is similar to an upper triangular matrix with all diagonal entries equal to 0. That means, that means a nilpotent matrix is equivalent to an upper triangular matrix with all diagonal entries equal to 0. Now, what is diagonalization? About A nilpotent matrix is not diagonalizable unless it is the 0 matrix. That means a non-zero nilpotent matrix is not diagonalizable. So, out of all the nilpotent matrices, the 0 matrix is the only nilpotent matrix which is diagonalizable. What can you say about similar? Say, if A is a nilpotent matrix, A is similar to another nilpotent. That means, if A is nilpotent and P is invertible, P inverse AP, and A and P inverse AP are similar to each other, and this P inverse AP is also nilpotent. Right. What can you say about the sum and the product? The sum and product of nilpotent matrices need not be nilpotent. Lastly, we talk about Jordan canonical form of A, which is very important for you. The JCF of A consists of the direct sum of Jordan blocks of the form JM0. In our case, we are talking nilpotent matrices, therefore all its eigenvalues are 0, therefore we are talking about JM0, where each block corresponds to the eigenvalue 0 of A. The largest Jordan block in our case has size k. Why? Because the index of the nilpotency of A is k. Because the index of nilpotency of A is k, the largest Jordan block has size k, and hence its minimal polynomial is x to the power of k, where k is the index of nilpotency. Thus, the Jordan canonical form of A can be written as Jm1, J suffix m1 bracket 0, direct sum of Jm2 0, direct sum of Jmr 0, where m1 greater than or equal to m2 greater than or equal to etc. greater than or equal to mr. What are they? They are positive integers. And how are they? When you sum it up, you will get n. And since our nilpotent matrix is of index k, one of them must have the order k. That means one of these m1, m2, mr must be k. So let us say satisfy m1 is equal to k. m1 is equal to k is coming because our matrix A is a nilpotent matrix of index k. Therefore, one of them must be k. And that is the largest one. Therefore, in the beginning itself it should come. Therefore, m1 is equal to k. As an example, an illustration is here. The possible Jordan canonical forms of a nilpotent matrix of order 5 with index 3 are J3 0 because index is 3 plus circle, J2 0. One of possible one of them. The other is J3 0 plus circle J1 0 plus circle J1 0. So two Jordan blocks of size 1. Here one Jordan block of size 2. So these are the only two JCFs that are possible for a nilpotent matrix of order 5 with index 3. Right. So that's how you have to make a notes on anything that you have come across in that question, concepts, results, so on and so forth. You have to make a notes like this. This is an illustration that I am giving it to you, a model to you. For each question, you make such a kind of a notes for you, and that will be helpful in the examination. With these few words, I say, I am sure that you have understood the solution of this problem. Thank you for watching my video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. I am sure that I will be meeting you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.